Hi, welcome back. Now we're at Foundations Python, Python Overview, and Common Use Cases. My name is Dennis. Let's go ahead and get started. Our learning objectives for today includes understanding the Python background, the interpretive language distinctions between that and compiled languages such as the C family. We want to identify where Python fits into other programming languages and their ecosystem, as well as the best use cases. We'll also be able to identify and install the basic interactive operators. I actually utilize them, such as multiplication, division, assignments, and many others to come. So let's start off with programming overview. Programming in general means that you're actually utilizing high-level programming languages such as Python, C++, C Sharp, .NET, whatever your heart's content. The idea is that you're creating something and programming, right? Providing instructions and sequences to the actual computer that actually needs to execute what your program is. So, language levels include high level, low level, and of course, machine code, which is ultimately binary ones and zeros. High level, which you might see over here. Let's go ahead and take a look here. Oops, let's go back here and try that pin one last time. There you go. High level first. So high level programming languages are usually the ones that can use plain English. We want to say, I want to use this. I want to print hello world, for instance. Those are symbols of high level. In this case, what you see here is that we're creating a function or a class specifically, and then utilizing a float definition or float function right here. And then we're going to return the triangle kind of formula and what you put in there. A low-level programming language is really something like assembly, where you don't really have a good idea of what's going on from an English standpoint or a human readable standpoint. These are assembly codes that have been extracted from the ones and zeros that are machine code to become something slightly more readable. So when you utilize low-level programming languages like assembly, it's usually because you're reverse engineering something or programming something that works at the hardware layer, perhaps utilizing something in memory or directly writing to memory. The equivalent of what you see at the top is the low-level program at the bottom, loading things into the registers and actually returning some sort of function. Also, we'll have executable machine learning code, or actually machine code by themselves, which is zeros and ones only. When we talk about computers being base 2, that's what we really mean. Throughout the scope of this course, you'll actually be utilizing high-level programming languages, and that's what we use today for the most part. When you get deeper into your career, such as being a professional reverse engineer, cybersecurity professional, or software engineering professional, or even perhaps hardware engineering professionals, that's when you'll start learning about low-level programming. For now, we'll stay at high-level programming languages to make it easier to understand as well as master the coding skills that you'll need in your DevOps career. So really, when we say about high level versus low level, we really mean abstraction. So for instance, we'll be learning Python. That's how you print hello world. One line, that's it. And it's using a print function. Very simple to do. However, in C, C is actually a middle kind of, it's supposed to be high level, but it's actually a middle layer programming language. Somewhere between low level and high level. And here, to do the same exact thing, we have to create so much more code. At least 3 lines. 1, 2, plus the bracket, and then 3 and 4. So almost 5 lines of code directly just to print hello world. And we have to initiate the function, import a library, in this case, standard io.h, which is a header file. And then we got to return from the function a status code of 0, which means we're successful in there. Ultimately, extractions are just saying we want to get away, further away from ones and zeros. How do we flip those switches inside your circuitry inside the CPU? All those electrical ones and zeros mean something. Having a high-level extraction programming language helps you out quite a bit. Now, if you want to see low-level programming languages, what is the equivalent of hello world? Well, here it is, assembly. Now, again, we're not covering assembly, and we're not going to be covering low-level programming language, but I wanted to give you a clear distinction of just how much work there goes into creating high-level programming languages. Now, when we say high-level programming languages, we also really mean that we're saying we're extracting away from assembly as well. Now, this is assembly in x86-64 Intel architecture. Now, below, let's try to get ourselves a clear picture here. And what we have here is our hello world message being queued into memory. We'll also see that we're setting up what's called a stack frame in memory right here, which we'll learn much later in the course about regarding security and buffer overflows. But really, all you're doing is loading different bytes of code, different perhaps data inside memory to CPU registers that actually execute that code in sequence. So all that print hello world that you saw earlier, which is essentially in Python, right? Python, we said print, and then we had hello world. And naturally, I'm not a great artist in terms of written language, but that's why we type fast. So Python print hello world is equal to all of this. So give you a closer examination and appreciation of low-level languages as well as the machine language ones and zeros, which would be even more crazy looking than this. In tandem, we also have two different types of programming languages at the high level at least. We have compiled, which is the C family, C++, C, C sharp, and we have Go, which is the Go language, also known for many different interesting replacements. It was actually made for a replacement for C family in general, as well as Java. We have interpreted languages such as Java, Python, and Ruby that relies on an interpretative engine. So instead of compiling your code, you're actually going to go ahead and utilize your script or your source code and run it through a what's called a virtual machine runtime. Right? The virtual machine runtime acts as your version of a real-time compiler, creating machine code that your actual computer can execute from the operating system. In essence, compiled means higher performance because you're compiling it directly to that architecture, starting from your source code, going all the way through your object code, and then finally becoming machine code, which is ultimately executed. Interpreted code has more portability as an advantage. So instead of having compiled code for Linux, Mac, and Windows, you could have one set of code that will operate across all different operating systems as long as you have the interpreter installed. The interpreter actually creates intermediate code or byte code. That's something you don't see. All you're supplying is source code. You don't do anything else. The Python interpreter, for instance, does all the rest right here behind the scenes without your knowledge. But there's a catch. Because you didn't compile that code up ahead of time, you're paying for it at runtime, which means your performance suffers in according with that. This is assuming that your code from compiled as well as the interpreter code are both equally efficient. Now, some of you are wondering, what about .NET? We hear about .NET all the time. Well, here's the interesting about .NET when we say it. .NET is actually not a programming language, but an intermediary language. Whoa, here. What do you mean, Dennis? So an intermediary language is actually a language that sits as a sandwich between the machine code as well as an interpreter and any other kind of compiled code from a high level. So take this Visual C# project, for instance. We have the high-level languages right here, and dependencies and references. And we might compile that into an exe inside Windows to execute. But using the .NET framework, the exe actually calls the .NET framework API functions. And so what you're actually doing is you actually have a bootstrap loader exe asking and acting like an interpretative language. .NET will use those .NET framework classes to call back to Windows system APIs. What does that mean to you? It means it does special things on the back end to make it easier for programming languages. And because an exe will always run under Windows, the .NET framework, as long as you have that installed, allows the exe code compiled into intermediary language code right here, using .NET to call that actual Windows backend function, such as writing to disk, opening a file, something of that nature. Ultimately, .NET is an intermediary language, so IL. It uses a just-in-time compiler right here at the .NET level, and it's lower performance in terms of actually a compiled true C# application by itself without using the .NET framework. So you can think of the .NET framework as a series of another layer as an interpretive language as long as your compiler or your C# project uses the .NET framework. Now, if you don't use the .NET framework and you call Windows System 32 API backends directly, that's going to be a native compiled item here, and it will run faster. However, if you want to make it easier for yourself, you can always use a .NET framework instead, but the catch is you're going to be running just like an interpretive language in terms of performance. So, what is .NET as a closure? Well, it's kind of both, right? You have a compiled binary that references some other APIs, and you have, honestly, sometimes the best of both worlds, or depending on how you write your language and your program as a whole, the worst of both worlds. Ultimately, the reason why you want to use .NET for binaries for Windows compatible systems is because it's deeply integrated with Microsoft. So, for instance, if you're a compiler, let's clear this real quick. If your compiler was just using, if I can get that pin to go back. There we go. Nope. Let's try that one more time. There we go. If we're just going to use Windows API calls directly from the C#, axing out .NET framework, it's a straight up compiled application, runs with the highest performance possible as long as you're being efficient with your code. The catch is, even though you're going to lose some performance, if you reference the .NET framework, technically different Windows operating system versions with the same .NET framework version, right? The same major version. So those of you who are a little bit old, just like me, Windows XP, Windows 2000 rings a bell. But what about Windows 10 and so forth and what's beyond? As long as they all have the .NET framework and you're compiling your code to utilize the lowest possible framework number, really, you can have backwards compatible code running from legacy XP all the way to Windows 10 using the same calls, which makes it really nice for programming. No need to recompile, no need to reconfigure. That's the advantage. However, you have a portable executable that references, and you have the same kind of advantages as you would with a scripting or interpretative type program such as Python, as long as you're going between Windows or Microsoft products in general. So, if you ever thought about programming an Xbox, a mobile device, or just Windows as a whole, .NET framework is what you want to use as an advantage. Now, when I say intermediary language and just-in-time runtime compiling, I really do mean that. It's not actually a compiled language. The reason why is you can use something like .peak or other decompilers on a .NET enabled binary. So, for instance, right here, I use this high-level programming language in C# that uses .NET calls. You can decompile it into a intermediary language and see that really almost in plain English that you actually have .NET calls doing something very similar. Now, these .NET calls right here make it easier for the programmer to actually utilize these calls versus this. So, which one's easier? Obviously, the high-level edition with the .NET framework, or you can use different calls directly native to Windows right here directly. The decompiler will actually show this for you and translate this information. Again, .NET is a hybrid model, not just one or the other. Now, native compiling, like C#, C, or C++, will have the source code, and you might have a compiler like GCC. The compiler will take this, turn it into assembly code, and then the assembler, which is usually a second component, and in GCC's case, it's all in one. Right? GCC is all in one right here. You don't actually have a compiler and assembler that links the assembly code to another library file. Now, in traditional Linux fashion, GCC will already be installed. However, for Windows users that want to use the same thing, you'll want to use MingGW, which actually acts as a C compiler and linker all in one. Most modern compilers, such as GCC and MingGW, will be an assembler, linker, and compiler all in one. So if you actually have object files, which are libraries essentially, you can link them inside or reference them as a dynamic linking with your executable, or statically link them together, ingesting this data directly in there, but also making your executable less portable, making it larger. Ultimately, native compiling just means saying, I'm not going to use an intermediary language or interpretive language. If you execute the code, it either runs or it doesn't. And hopefully, if you have dynamic libraries reference versus a static compiled binary, you have those libraries on your system, making the executable smaller. Now, why would you use a dynamic compiling library? Well, you might use it because you want to reduce your size, your overall footprint, especially if Windows OS perhaps had WinSock DLL, and every Windows OS should have that. However, when you're running into situations where a DLL is not going to be standard on an operating system, you might want to include it as a static compile or be part of your installation process. The syntax for compiling C code is GCC source-code.c -o for object or output, and your binary name for Linux ELF files. Windows uses PE files, which means portable execution. All right, so let's get back to our next slide here. What are some common languages? Well, we talk about Python in this course, but there's many others, right? We just mentioned C. We don't mention we have Fortran, which are old languages, Pascal, BASIC, SQL, Objective-C, which uses for your iPhone applications. Many different others have come and go along the way. Just know that as you grow as your profession, additional languages will come out. Additional languages will be going out of style as well. And while you may know one language really well, you're going to know other ones as well. So it's really important for you to grasp the programming logic behind everything, or structures, and how programming actually works is equally important to understanding Python and the Python syntax by itself. Let's continue. So all about Python. Again, interpret it, but the use cases include strong science and machine learning library support. And the best part about it is automatic memory management. I don't want you to worry too much about what you see on the left here, but just know that this is what Python kind of looks like. It's really simple to kind of follow when you look at it a little bit closely. We have comments, we have imports of libraries, we have if statements and elif, and then we also have functions that you can call and redirect. This is my personal custom sample code on looking for different what's called personally identifiable information in the cyber realm, or looking for PII for short. It looks for regular expressions related to social security numbers, perhaps healthcare medical record numbers. All those are defined in my function, which I can utilize as kind of a data discovery item. Python itself started in the 1990s with a large community backing. Again, large community backing recently in AI and data analytics. It's designed to be considered a beginner-friendly and general-purpose language. So, why would you use Python? It's a good starter language, and you can use it for a lot of different things. And if you ever want to go into data science, well, there's a lot of libraries that support that, including Google's TensorFlow. Now, C# is part of a later version of C families, so C, C++, Objective-C, as well as C# became the past. Now, C# also is an interesting language that you might see over time. It's compiled, but was originally released with the Microsoft .NET framework. It's a general purpose language in whole, and it's actually event driven. So it's modernized to say, hey, if you send me an event, I can queue it up, or I could provide it back to you without having you worry about that call being returned back to you synchronously. Now, it was created in the 2000s, and again, part of the original .NET 1.0 framework, and was influenced by different syntaxes related to C, C++, and including the Java family. Anything related to C# provides native integration inside Windows and Windows-like programs. And I also mentioned SQL, which means structured query language. Some don't consider this a programming language, but really it is. It's got a sequence. It's got information right here. Let's go back here and get my pen back here. Right? It has structure related to it and provides inputs and outputs, and you can create functions in there. It's still a language, and it's not programming a very specific program, but it's related to data and databases, which you use commonly. It's relational and transactional focus, and relies on a database management system such as Microsoft SQL, Oracle, and MySQL Server as well. Remember that SQL focuses on the transactional and relationship side. It's also known for CRUD operations, which is create, read, update, and delete against data objects. Now, SQL was originally developed in the 1970s and was originally, ironically, introduced by Oracle, even though some of you may only use Microsoft SQL Server. Now, as you're thinking about programming languages and what it takes to actually run a program, you need to think about runtime. What is a runtime environment? What is a runtime in general? Python code uses the interpretative language, right? So it uses an interpreter, which is a virtual machine, PVM for short. There's a syntax and language translation to make sure that we error out before we even try to execute code inside the operating system. Translates into bytecode and gets into the virtual machine portion and creates the output accordingly. So the Python binary right here is a interpreter. When we add our input data, which is hello world@py, and we have hello world as our print statement. That's really all there is to it. Now, that was a lot of information. Let's take a quick break and then come back and lecture about our second topic of the day. Hi, welcome back. I hope you had a great break. Let's continue on. Let's start with Python as an overview, not just about a high-level conceptual theory about programming, but actual Python itself, what goes into it, what you can do with it, and some of the example code, and we'll start off now. So Python, just like every other programming language, has a syntax structure. That syntax structure is available to follow so that the computer or the interpreter will actually understand what you're trying to tell it and then convert it into the bytecode needed for machine code ultimately. Utilize syntax to run applications and commands in it, and really is part of the whole programming language as a whole. Distinctively, Python uses def for definitions or aka functions. We have an add 5 function here, which is take any input of x and return +5 to it, which is right here. Let's go to pin. There you go. We also have a dot write, and don't worry too much about what is going on here, but just understand the syntax. We have a keyword, we have the parameters that go with it, and if you're a function, you must end the block with a colon, but not required of every line. Again, you have functions and other keyword statements that turn different colors depending on your code editor. We can have if-else statements and other conditional branching information to help you run your program, providing it logic and other great things that you need to use while you're developing in Python. Now, what about function execution? Well, what's the function in this case? This function name is function name is print. Print. And then here are my parameters, my input. That's what it provides back to me. That's all really is to it. So what is a function as a whole? Well, remember, a function is just a encapsulation of a sequence of events, getting something to do something for you, taking an input and producing an output, or performing actions with an input. Again, functions are just that simple. Provide something in, get something out. We also want to create variables. Now, Python and many other languages would be very hard to actually program anything if you had to say Dennis for every name, and then you have to program the actual name for every place, right? And instead of saying X equals Dennis or X equals Becky, really, those what variables are needed for. Otherwise, you'd have to have my name referenced each and every time statically. It could make for a very large program and highly inefficient. So how do you create a variable in Python? Well, Python variables are actually quite simple. You have the actual variable name, and then you have equal sign, followed by the right side of it, which basically says, hey, assign this variable. In this case, I want to say a equals 2. I can also add variables together with other numbers because it's an interpretive language, and it evaluates it accordingly automatically. So a is now equal to the original value of 2 plus 1, and now a is equal to the ultimate value of 3. Of course, I want to say b equals 2. A is still 3, right? So you can have multiple variables at the same time. Now, the important thing about variables is that it's a variable name on the left side. On the right side of the equal sign, you have a value. It's case sensitive, and you cannot have spaces, which means you might use an underscore. And remember, variables are always mutable, which means you can change them at any time, which could be a good thing or a bad thing depending on your functions. Now, Python is designed to work in many operating systems. Earlier that you learned inside Linux, Linux is case sensitive. So, saying lowercase print is not the same as saying uppercase print. And it'll give you an error accordingly. Again, case sensitivity. Each case is a distinct version, and be careful when you're naming variables. Check the error messages every time you see something to understand what's going on here. In this case, there is no such thing as P, capital P for print. We want a lowercase p in this case. Indentions are also special in Python. Some languages don't require indentions or don't need them. Python is indention sensitive, just like case. So if you create a block that has a condition such as if x is less than y, so also known as saying if 10 is less than 20, then do this because it's always true, which means print always true. Now, if I take away the indentation, notice the indentation right here. Let's clear the screen. Without that indentation right here, stick it away. Now we have an indented block error at line 7. Okay, line 7. Now, an indentation is not equal to spaces. You have to use the actual indentation key, the tab key on your actual keyboard. You want to have one indentation per statement. So if you have multiple nested loops, nested if-else statements, you gotta have indentions accordingly with them. So think of indentions as always required when you have a keyword statement that has a decision-making requirement, branching out from if-else or even a loop. Now, comments include single-line and multi-line comments. Comments don't execute code, they're just there for notes or perhaps code that you were using for troubleshooting or debugging at some point, and you might want to keep it there for later on. You have comments that are multi-line using 3 ticks at the top, 3 ticks at the bottom, and all there in between those 3 ticks, or those 6 ticks as a whole, it's all commented out. You can have a single line comment, which uses a pound sign in front of it. And most code editors will actually turn that green. The interesting part about Python, unlike some other languages, is that you can have inline comments at the same time as your actual running code. Python doesn't care, which is really cool. So that means instead of just putting it at the top, saying what this code might do right here, why don't you put the actual statement of what the code is actually doing right there in the same line? Again, kind of special to Python, not always the case with every programming language. Another thing to note is that when you import libraries, instead of you doing everything from scratch, like for instance, if you want to take a function that is going to calculate the angle of a triangle, a right triangle, or the total area of a triangle, well, those are known mathematical functions in geometry as well as trig. Other programmers have created these functions for you, so why reinvent the wheel? So, package management. Python is an internet-enabled programming language. By default, it has a community-based package management session called pip, which essentially downloads packages for you from pythonhosted.org. And that's what it looks like if you actually punch that into the browser GUI window. Just know that if you know there's a package out there that already does the work for you, no need to reinvent the wheel. Now, the only stickler behind this is that, remember, all the modules uploaded to this community base is not scanned or checked or validated. That's still up to you from a security perspective as you develop further. Now, Python also has a built-in module called venv, which really means virtual environment. What you're trying to do is instead of downloading and installing the operating system level dependencies and junking up your system, take everything for that one program and download it to a folder. Now, what you could do is have app 1 in folder 1, app 2 in folder 2, and app 3 in folder 3 without having ever downloaded any of the items inside your operating system. That way, you're truly portable, and again, encapsulates everything inside a folder. When you get to containerization and serverless compute, which you'll learn much later on in this course, or perhaps earlier on, you will understand that virtualized environments are really good to have and really the best practice. If anything else that you take from this course, from Python, as you program something, always do your best to use a virtual environment with Python. Put all your dependencies, all your eggs in this case, in one basket. This is going to be helpful for you as you get to a containerization mechanism later on in this course. How do you set up a virtual environment? Well, concepts are the same thing that we just talked about. With Python, you can use an inline module mode with -m, and you can actually create a folder within your current folder. So here, you can see me going into using the venv module. I go into the folder next, and I use what's called a activation of a virtual environment. In PowerShell and Windows, I use a dot, prefacing it with the script. Okay? Dot space and then the script, which is activate that PS1 in my case, will give me into a virtual environment. Now, if you go back to how do you know you've activated your virtual environment? Well, look at the change in your prompt right here. Might change colors, or it just might say, hey, my app-inf virtual environment. And there you can install all your different tools inside that folder, all encapsulated based on what you need. Now, on Linux and Mac, instead of using a dot, you'll use the term source, which is a command separately provided to you. Now, Python includes many different built-in functions because they wanted to make it flexible and ready to use out of the box. Now, some of these might be recognizable, like the absolute value function, any value if it finds it inside an iterable or a list, converting something from an object mode that your computer can understand to something that we can understand from a text-based perspective. Create different arrays, different data structures, and even look at a directory listing of all the methods you have in a certain class. So basically, list all the functions that you have in a group of functions. I won't read all these out loud to you, but remember, read your documentation and look at all the great things that Python has to offer, such as int, which is returns an integer number, take input from a user, turn something into hexadecimal, and many others. We also have integer numbers, lengths, strings, all kinds of different types. Again, take some time to read the documentation and go through everything. Or review each portion of the slide, click on the links, and try to figure out what each function does. Don't worry, we'll have different examples as we go through the entirety of this course. Again, more built-in functions, and we want to sum things like we have lots of good stuff around numbers, input and output, and also reverse a string of characters. Very cool stuff. Some of it you'll be utilizing a lot, some of them not so much. Again, part of every important portion of being a DevOps and developer in general, read the documentation. I can't stress that enough. Here's examples using some built-ins right now. You already saw print. What about a list of numbers inside a list? So every time when you say the word list, think of square brackets. Put anything in that list, numbers, characters, whatever. You also sum a list of numbers inside a function and print that back out. So between 1, 2, 5, 10, -1, 0, 100, and 247, the sum of all that is 364. Harder to do in your head as a human, quite easy in programming. Notice that we use our inline comments right here if we so desire to choose. So Python in general also includes math operators. These math operators are what you might remember from the grade school, pin dots. Oops, get our pin back here. Pin dots, at least that's how I learned it back in grade school, right? Exponentials, multiplication, division, addition, subtraction, yeah. Does that all make sense? Powers? Well, they're all back here. And instead of using a caret that says, hey, I'm going to use something up here, I use a double star. Otherwise, everything else looks pretty familiar. You can also use floor division with a double / as well. And if you wonder what modulus is, well, that takes the remainder of something. So if you said back in grade school, hey, some uneven number divided by whatever, what's my remainder? The percentage sign provides the remainder of x modulus y. Here's an example of some math operators in use with our built-ins. 10 plus 1 is 20. 10 divided by 2, we use in parentheses, times 5. 5 times 5, 25. Notice something interesting here. We have an integer right here, but we have a float right here. A float is simply something with decimals. Okay? That's all it really is. Just keep that in mind in the back of your head. We also have logical operators. So true, false tables, something that comes out of nature if you were in grade school. Not, that's okay. When we're making comparisons and we're looking at branching conditions such as, hey, should I do that If this, well, you'll use a logical operator in most cases. X equals to y, not equals to, greater than, less than, greater than or equal to, and less than or equal to. Very common functions. Again, go ahead and look. We'll use plenty of examples throughout the course, but feel free to look at the documentation as well. In an example right now, we're assigning two different variables, two different strings. Print is string 1 equals to string 2, the exact value. And of course, it's going to come back as false. The string 1 not equal to string 2? Yeah, that's true. What about this? Is 10 less than 100? Yeah, that's true. So if you don't provide anything else, an if condition or any other statements, if you make a comparison statement operator, you're always going to get a true-false return. Keep that in mind as you're programming. Lots of ideas should come forward when we start getting deeper into our code. Let's take a quick break and do a demo as well of some of the functionalities inside Python. We'll see you in a bit. Hi, and welcome back. Hope you had a great break. Let's go ahead and use a quick Python environment. Here I'm using REPL. You can use whatever you wish, such as VS Code or the standard command line interpreter, up to you. First thing to note is that we have let's actually make this a little larger. All right, that's a little bit better. We'll use what's called a shell bang. So we have pound and exclamation point, which usually says shell bang. And we provide the actual path to the Python 3 binary, which is our interpreter here. Okay, so let's go over some of the concepts that we saw earlier. Well, how do we assign a variable? Take a moment, think about it, and get back to me. All right, did you think about it? Okay, so if I want to assign a value of 100, that's how I would do it. And the spacing actually doesn't matter, right? I can actually say a now equals to 2. Now, knowing that you have two of these statements together, logically, what is a now? Is a 100? Is a 2? Or is a 102? The answer is a equals 2 because that is the next statement. To prove it, I'm going to click run. And as it spins itself back up, I'll just say, hey, what is a? That's the value of 2. You can also see what type of the data it is by going type and a, which is the variable here, and it's an integer type. If I wanted to turn it into a float, I might use a built-in function like float. So I'll do float a, and just for the sake of making it simple for first-timers, put a pound sign in front of it, making it a comment only. Run it again. We'll make a float. Now we have a. Well, it's still 2. We'll do a type a, and it's still an integer. What happened? Well, it's because we didn't assign float, the output of float, into a variable. It just returns it back to us. So if I went float of a inside an interpreter portion, now I get 2.0, which means anything with a decimal is always a float. To make that stick, we'll say a is now the same variable, or I can always say b or c. We'll just say c. Run it again. Now c is 2.0. So those are the main items of just basically doing this. What are some other built-in functions that we could do to make ourselves showcasing that we're having useful items? Well, let's go a little bit deeper into this. I'm going to use some boilerplate code here. And I'm going to paste it right here. Let's go over it really quick. And I didn't paste it correctly. Remember, we have indentation issues. This needs an indentation. This needs an, oops, that's 2 indentions. And this needs an indentation. See where you see this blue here, right, this keywords? You need an indentation right behind them. I'm going 1 level deep. There we go, no more red, which is good. Let's start from the top. Comment says student input. So take the input of a student input 0 through 10 and then turn it into an integer. Assign that integer to score and hold that integer inside the variable score. If score is above 5 and score is less than or equal to 10, print Dennis is above average. Now, this is assuming you're rating Dennis, me, as a teacher. Else if score is less than 5 and score is greater than or equal to 0, Dennis is a below average instructor. Sad face. Condition for at least 5? Well, if we're exactly at 5, so if I said 5 here, Dennis is just plain average. Else, which means if nothing matches from above right here, print Dennis is a smart Alex student. Well, maybe Dennis is not, maybe you are. Who knows? Let's give it a shot. Let's use 100. Aha. Right, I'm smart Alex because I'm not within the realms of 5, greater than 0 or less than 5, and the upper bounds of 10 and greater than 5. And of course at 3, well, below average instructor. So you can see here that the interesting part is that as soon as I enter a number, right? If I enter a number right here, it's going to save it into the score, and now I can reference this 3. 3 is greater than 5, but less than 10. Not the condition I'm looking for. But I'm less than 5 and greater than 0. This is where I stop and do this stuff. Okay, that's it for now. Go ahead and go to your labs. Take a quick break if you wish. See you in the next lecture.